Welcome to this problem-solving session. In this video, we'll tackle LeetCode problem number 949, titled Largest Time for Given Digits. This is an interesting challenge that tests your understanding of permutations and logical reasoning. Let's dive in and explore how to solve it step by step. In this problem, you're tasked with finding the largest valid time that can be created using exactly 4 digits provided in an array. The time must follow the 24-hour format, meaning that the hours can range from 00 to 23, and the minutes can range from 00 to 59. If it's not possible to create a valid time using all 4 digits, you should return an empty string. The input will be a list of exactly 4 integers, each ranging from 0 to 9. The output should be a string representing the largest valid time in the format HHMM, or an empty string if no valid time can be formed. For example, if the input array is 1, 2, 3, 4, we aim to determine the largest valid time that can be constructed with these digits. The output for the input, 1, 2, 3, 4, is 2341. Here's how we arrive at this result. First, we generate all possible permutations of the digits in the array. Then, we check each permutation to determine if it forms a valid time. Valid times must have the hours between 00 and 23, and the minutes between 00 and 59. From the permutations, valid times include 1234, 2143, 2314, and 2341. Among these, 2341 is the largest, so it is returned as the result. On the other hand, if the input is 5, 5, 5, 5, all permutations will fail to meet the criteria for valid hours and minutes, so the output in this case is an empty string. For the input, 5, 5, 5, 5, no valid time can be formed because the digits do not allow for hours between 00 and 23. All permutations of these digits fail the conditions required for valid hours and minutes, so the output is an empty string. Now consider the input, 0, 0, 0, 0. Here, the only valid time that can be constructed is midnight, as the digits successfully form a time within the allowed range. This demonstrates that even when all digits are the same, we can still form a valid time if they satisfy the rules for 24-hour formatting. There are a few important constraints and edge cases to keep in mind. Each digit in the input array will always be between 0 and 9, and you must use all 4 digits exactly once to form the time. The time must adhere to the 24-hour format, where hours range from 00 to 23 and minutes range from 00 to 59. In some edge cases, like when all digits are too large to form valid hours or minutes, for example, 9999, you should return an empty string. If the digits allow for only one valid time, such as 0000, you return that time. If the input contains duplicate digits, like 2222, ensure all valid permutations are considered. Lastly, when some permutations are invalid because they exceed the allowed range for hours or minutes, filter them out and return the largest valid time from the remaining options. To solve this problem, we start by considering the brute force approach. The intuition here is straightforward. We generate all possible permutations of the 4 given digits and then evaluate each permutation to see if it forms a valid time in the 24-hour format. For a time to be valid, the first 2 digits must represent hours between 00 and 23, while the last 2 digits must represent minutes between 00 and 59. Once we identify a valid time, we calculate its total value in minutes since midnight using the formula hours * 60 plus minutes. This allows us to track which time is the largest. Finally, the largest valid time is converted back to the HHMM format for the result. The process involves 4 key steps: generating all 24 permutations of the digits, validating each permutation as a possible time, tracking the maximum time in minutes, and returning the largest valid time as a formatted string. When analyzing the complexity of this approach, we note that generating all permutations of 4 digits takes O(4), which is a constant 24 operations. Validating each of these 24 permutations is an O(1) operation, as we are simply checking numerical ranges for hours and minutes. This makes the overall time complexity O(24 by 1), which is effectively constant. While the brute force method is exhaustive, the small input size ensures it remains efficient. The main advantage of this approach is its simplicity and guaranteed correctness, as we systematically evaluate every possibility. However, the trade-off is that it relies on an exhaustive search, which, while manageable for this problem, could become impractical with larger inputs. The optimized brute force approach builds on the simplicity of the brute force method while introducing improvements to streamline certain operations. This strategy works well because the input size is small, and we can efficiently validate times without repeatedly converting digits to integers. One key optimization is performing inline validation for hours and minutes directly, eliminating redundant calculations. For example, we directly check whether 10*A plus B falls between 0 and 23 for hours, and whether 10*C plus D falls between 0 and 59 for minutes. Additionally, using string slicing improves clarity and readability in the code. The steps remain largely the same: generate all permutations of the digits, validate each permutation using these inline checks, track the maximum valid time, and finally convert it back to the HHMM format. Despite these optimizations, the overall complexity remains 24, as the number of permutations is fixed. Several key observations reinforce why this approach is effective. First, the limited input size, just 4, makes the brute force method viable. Second, finding the largest valid time corresponds to maximizing the value of hours *60 plus minutes, which is straightforward to calculate. Inline validation further reduces computational overhead, making the process more efficient. This approach was chosen for its simplicity, as it avoids unnecessary complications while still being efficient due to the fixed number of permutations. Alternatives like sorting-based construction or greedy methods were considered but ultimately deemed less suitable. Sorting-based construction, while logical, involves additional complexity for validating time constraints. Greedy construction, where we iteratively pick the largest possible digit for each position, is prone to errors due to interdependencies between placements, for instance, ensuring hours remain within 23. These complexities make the optimized brute force approach the most practical choice. In conclusion, the optimized brute force approach strikes the right balance between simplicity and efficiency, making it the best solution for this problem. The small input size ensures the time complexity remains constant, and the optimizations introduced reduce unnecessary calculations and improve clarity. While alternative strategies could be explored, their added complexity isn't justified given the constraints of the problem. By systematically evaluating all permutations and leveraging direct validations, this approach provides a straightforward and effective way to determine the largest valid time from the given digits. The problem asks us to determine the largest valid time in the 24-hour format from 4 given digits. A valid time must adhere to strict rules. The hour part, represented by HH, must fall between 00 and 23, and the minutes, represented by MM, must fall between 00 and 59. To solve this, we need to explore all possible arrangements of the 4 digits to check for valid times. Since there are 4 digits, we can generate all possible permutations. There are 4 or 24 unique orderings. For instance, if the digits are 1, 2, 3, 4, the permutations include sequences like 1, 2, 3, 4, 1, 2, 4, 3, and so on. Generating these permutations ensures that no possible combination is overlooked. Once we have all the permutations, the next step is to filter them to identify valid times. For each permutation, the first 2 digits form the hour, and the last 2 digits form the minutes. For example, the permutation 1, 2, 3, 4 corresponds to HH equals 12 and MM equals 34. We check whether HH lies between 0 and 23 and MM lies between 0 and 59. If either condition is not met, the permutation is discarded. For valid times, we then compare their total minutes since midnight to track the largest time. This is done by converting HHMM into total minutes using the formula total_minutes equals HH*60 plus MM. By maintaining a variable to store the largest total_minutes, we can efficiently compare and update as we iterate through the valid permutations. After filtering and tracking the maximum valid time in minutes, we need to convert it back into the HHMM format for the final output. This is done by reversing the total_minutes calculation. The hour is obtained by dividing total_minutes by 60, and the minutes are the remainder when total_minutes is divided by 60. The result is then formatted as a 0-padded string, such as 2345. If no valid time is found, meaning no permutation satisfies the constraints, the function should return an empty string. The key insights here include the use of permutations to ensure all possible orders of the digits are checked and the conversion of times into minutes for straightforward comparisons. This approach eliminates ambiguity when determining the largest time. When designing the algorithm, it's important to handle specific edge cases. For example, if the digits are 9999, no valid time can be formed since 99 is not a valid hour. Another scenario involves multiple valid times from the same digits, such as 1, 2, 3, 4, which can form both 1234 and 2341. The algorithm ensures that the largest, 2341, is chosen. Additionally, leading zeros must be handled correctly. 4, 0, 0, 1, 2, the output should be 2100 hours rather than 920. From a data structure perspective, we use a list to store the permutations, an integer to track the maximum time in minutes, and a string for the final formatted output. These choices ensure the algorithm is both efficient and easy to implement. Finally, let's analyze the complexity of our solution. The time complexity is dominated by the generation of permutations, which takes 4 or 24. Validating each permutation involves simple mathematical checks, which take 1 per permutation. Since there are 24 permutations, the total time complexity is 24, which is effectively constant time given the fixed input size. For space complexity, storing the permutations requires 24 space, and additional variables, such as the maximum time and output string, require 1 space. Thus, the total space complexity is also 24, which is constant. This makes the algorithm both time and space efficient, given the constraints of the problem. This implementation solves the problem by generating all possible permutations of the given digits and checking which combinations form valid times in the 24-hour format. Here's a step-by-step breakdown. 1. Imports. We use the permutations function from the itertools module to generate all possible orderings of the input digits. 2. Initialization. The variable max_time is initialized to -1. This will store the largest valid time in total minutes, which will be updated as we find valid times. 3. Generating permutations. The permutations function generates all possible arrangements of the 4 digits. For each permutation, the first 2 digits are combined to form the hour, hours, and the last 2 digits form the minutes, minutes. For validation, we check if the generated hour and minute values fall within the valid ranges. 0 equals hours less than 24 and 0 equals minutes less than 60. If they do, the total time in minutes is calculated, hours *60 plus minutes, and compared with max_time to keep track of the largest valid time. 5. No valid time. If no valid time is found after checking all permutations, the function returns an empty string. 6. Formatting the result. If a valid time is found, the max_time value, stored in total minutes, is converted back to hours and minutes. The F, max_hours 02, max_minutes 02, ensures the output is in the correct HHMM format, with leading zeros if necessary. This implementation is efficient given the constraints, as the number of permutations is fixed. 4 equals 24. Each permutation is checked in constant time, making the solution fast and robust for the problem's requirements. Here, we start by importing the necessary packages and defining our solution class. The method largest time from digits takes an array of 4 integers as input, representing the 4 digits. We initialize a variable maxTime to -1 to keep track of the largest valid time in minutes. Then, we generate all possible permutations of the array using nested loops. For each permutation, we calculate the indices of the digits and use them to form the hours and minutes. The key here is to ensure that we avoid using the same index multiple times by checking conditions like j == I and k == I, k == j. Now, once we have the hours and minutes, we validate them by checking if the hours are less than 24 and the minutes are less than 60. If the time is valid, we calculate the total time in minutes and update maxTime to store the maximum value we've encountered so far. After generating all permutations and validating the times, we check if maxTime remains -1, which indicates that no valid time was found. In this case, we return an empty string. Otherwise, we convert maxTime back into the HHMM format. To do this, we divide max time by 60 to get the hours and use the remainder to calculate the minutes. We then use string.format to ensure the result is properly formatted with 2 digits for both hours and minutes, even if they are less than 10. Finally, the formatted string is returned as the output, representing the largest valid time that can be formed from the given digits. To solve this problem, we begin with the input array 1, 2, 3, 4. The first step is to generate all possible permutations of these digits. Using Python's itertools.permutations, we can create 24 unique arrangements, such as 1, 2, 3, 4, 1, 2, 4, 3, and so on. These permutations represent all the potential orderings of the digits. Next, we start validating these permutations to determine if they can form a valid time in the 24-hour format. For example, the permutation 1, 2, 3, 4 gives 12 as the hour and 34 as the minutes, which is valid. We then calculate the total time in minutes, which is 12*60 plus 34 equals 754 minutes, and store it as our current maximum time. For the next valid permutation, 1, 2, 4, 3, the hour is 12 and the minutes are 43, giving 763 total minutes. This becomes the new maximum. We continue this process for all permutations, keeping track of the largest valid time in total minutes. Finally, the maximum valid time found is 23:41, equivalent to 1421 total minutes. Now that we have the maximum valid time in total minutes, 1421, the next step is to convert it back to the standard HHMM format. To do this, we divide 1421 by 60 to get the hours, which equals 23. The remainder, found using the modulus operator, gives the minutes, which equals 41. Combining these results, we format the output as the string 23:41. Moving on to another example, consider the input 5, 5, 5, 5. Here, all permutations are identical, resulting in 5, 5, 5, 5. When we validate this permutation, we find that the hour is 55 and the minutes are 55. Since hours must be less than 24 for a valid time, this permutation is invalid. As no valid time can be formed from these digits, the result is an empty string. Let's examine another example where the input array is 0, 0, 1, 0. By generating all permutations, we get combinations like 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, and so on. For each permutation, we validate whether it forms a valid time. For instance, 0, 0, 1, 0 gives 0, 0 as the hour and 10 as the minutes, which is valid. Converting this to total minutes, we get 0*60 plus 10 equals 10 minutes, so we update the maximum time to 10. Another permutation, 0, 1, 0, 0, gives 0, 1 as the hour and 0, 0 as the minutes, which is also valid. This results in 1*60 plus 0 equals 60 minutes, and we update the maximum time to 60. After validating all permutations, the largest valid time is 10:00, which corresponds to 600 total minutes. Finally, converting 600 back to HHMM format, we find the result is 10:00. To summarize, this solution relies on generating all permutations of the input digits to ensure that every possible combination is considered. The validation step checks whether each permutation forms a valid time in the 24-hour format, where hours must be less than 24 and minutes less than 60. By converting valid times into total minutes, we can easily compare and track the largest time. Once the maximum total minutes are identified, converting it back to HHMM format ensures the result is properly formatted and easy to read. This method guarantees an exhaustive and accurate approach to finding the largest valid time that can be formed from the given digits. To analyze the time complexity of our solution, let's break it down into its components. First, the solution generates all permutations of the input array, which contains exactly 4 digits. Using the itertools.permutations function, we know that the number of permutations for 4 distinct elements is 4 factorial, or 4, which equals 24. This means that generating the permutations has a time complexity of 4. Next, we iterate over each of these 24 permutations, so the cost of iterating is also 4. For each permutation, we calculate the hours and minutes, check whether they are valid, and update the maximum valid time if necessary. These operations involve basic arithmetic and comparisons, each of which takes constant time, or O1. Since this validation step is performed for each permutation, the total cost for validation is O4. Asterisk O1, which simplifies to O4. After validating all permutations, the final step is to format the maximum time into the HHMM format, but this is a straightforward constant time operation, or O1. When we combine all these steps, the dominant factor in the time complexity is the generation and validation of permutations, which together result in a time complexity of O4. Since 4 equals 24, this is effectively a constant for this specific problem. However, when expressed in terms of big O notation, the time complexity remains O4. Now, turning to space complexity, we begin by looking at the storage requirements for permutations. The itertools.permutations function generates permutations lazily, meaning it doesn't store all permutations in memory simultaneously. As a result, the space required for permutations is negligible. Additionally, the solution uses a few integer variables, such as max_time, hours, minutes, and others, to store intermediate results. These variables require constant space, or O1. We also need to consider the space required for the input array. Since the input array ARR always contains exactly 4 elements, the space required for it is constant, or O1. When we combine these factors, the overall space complexity is dominated by the auxiliary variables in the input array, both of which require constant space. Therefore, the total space complexity is O1. To put this in perspective, let's compare our solution to a brute force approach. A brute force method would involve generating all possible 24-hour times, from 00:00 to 23:59, and checking which of these can be formed using the digits in the input array. Since there are 1440 possible times in a day, this approach would require iterating over all 1440 times and validating each one. This results in a time complexity of O1440*k, where k is the cost of checking whether the time can be formed using the given digits. Our solution, however, avoids this inefficiency by directly generating only valid permutations of the input digits. The current solution is already optimized for this problem because it minimizes both the number of permutations generated and the cost of validation. Let's now look at the best, average, and worst-case scenarios for this solution. In the best case, the first permutation that is evaluated is valid and forms the maximum time. However, the algorithm still evaluates all permutations, so the time complexity remains O4. On average, the solution iterates over all permutations, validating each one, so the time complexity is still O4. In the worst case, no valid time can be formed from the input digits, which means the solution will still iterate through all permutations. Even in this scenario, the time complexity remains O4. This consistency across all cases highlights the efficiency of the approach. To solidify our understanding, let's briefly summarize the mathematical reasoning behind the big O notation. The number of permutations for a set of size 4 is 4, which equals 24. For each permutation, the validation and comparison steps take constant time, or O1. When we multiply the two components, the total time complexity is O4. Asterisk O1, which simplifies to O4. As for space complexity, since no additional data structures are used and the input size is fixed at 4 elements, the space complexity is constant, or O1. This balance of time and space efficiency makes the solution well suited for this problem. In this section, we'll discuss some common mistakes to watch out for when solving this problem. One frequent error is failing to validate the time format. It's not enough to simply check permutations of the digits. You need to ensure that the hours are within the range of 00 to 23 and the minutes are between 00 and 59. Skipping this step can lead to incorrect outputs or runtime issues because the solution might try to use invalid times. Another common issue is overlooking duplicate permutations. For example, if the input digits include duplicates, like 1, 1, 2, 2, you might end up generating the same permutation multiple times, which is wasteful. Fortunately, Python's itertools.permutations can handle duplicates automatically, so leveraging it can save you from unnecessary computations. Additionally, incorrectly handling leading zeros is another pitfall. Some implementations mistakenly reject times like 123, assuming they're invalid, but in the 24-hour format, leading zeros are perfectly acceptable. Lastly, failing to test edge cases, such as all zeros, 0, 0, 0, 0, or the largest valid time, 2, 3, 5, 9, can result in bugs that could have been caught with better testing. By explicitly addressing these boundary conditions, you can ensure your solution is robust. Inefficient permutation handling is another mistake to be aware of. Generating all possible permutations of the digits and only filtering them afterward can create unnecessary computational overhead. To address this, try filtering invalid hours and minutes as you generate permutations, rather than waiting until the end. This reduces the search space and improves efficiency. Now, when tackling this problem in an interview setting, keep in mind that interviewers are looking for more than just a brute force solution. They want to see if you can come up with an efficient approach while handling edge cases effectively. Start with a clear explanation of the brute force method, but then suggest optimizations, like pruning invalid permutations early. Always remember to test edge cases and ask clarifying questions. For instance, you might want to confirm whether all zeros are valid or what to do if no valid time can be formed. Finally, if you propose an alternative approach, make sure to explain the trade-offs clearly, especially regarding time and space complexity. This demonstrates both your problem-solving skills and your ability to think critically about efficiency. Let's explore some related problems that can help you build the skills needed for this challenge. First, LeetCode problem 46, permutations, is a fundamental exercise in generating all permutations of a list, which is directly applicable here. Problem 47, permutations 2, builds on this by introducing duplicate elements, making it a great way to practice handling repeated digits in your input. Another useful problem is LeetCode 31, next permutation, which focuses on generating permutations in lexicographical order and can be helpful for structuring your approach systematically. Finally, LeetCode 267, palindrome permutation 2, is another problem involving permutations under specific constraints, providing additional practice with the logic required to filter valid results. When considering alternative approaches, the brute force method is often the first that comes to mind. This involves generating all permutations of the 4 digits, filtering out invalid times, and returning the largest valid time. While it's simple to implement, its time complexity is 0, 4, or 24 permutations, which can become inefficient as input size grows. This makes it a good starting point for understanding the problem but not the most optimal solution. Another approach to consider is the greedy method. Here, you would start by sorting the digits in descending order and then attempt to construct the largest valid time by placing the largest possible digits in the hour and minute positions. This approach has a time complexity of O, n log n, due to the sorting step, and while it's faster than brute force, it can be less intuitive to implement, as you have to carefully account for validity constraints at each step. Lastly, there's the backtracking approach, which involves using recursion to build valid times step by step while backtracking whenever constraints are violated. The efficiency of this method depends on how effectively you can prune invalid paths during the recursion. While it may require more careful implementation compared to other methods, backtracking is often more efficient than brute force for constrained problems like this one. Each of these approaches has its own trade-offs, so the best choice will depend on the context, such as whether you're optimizing for clarity, efficiency, or flexibility. Great job! To summarize, we used permutations to solve this problem and focused on handling edge cases effectively. This is a wonderful example of applying logic systematically in problem solving. Thank you for watching, and don't forget to like, comment, and subscribe. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!